Hey, folks. Hey, for now, we're going to start circular dynamics, and this is an intro with an example. And for circular dynamics, if you understand Newton's laws in the previous unit, if you understand that well, circular dynamics is going to be fairly easy for you. Um, it's just an offshoot of Newton's laws and a specific example of Newton's laws. So stuff that we've actually already mentioned in the past, and I'll just reiterate it quickly, is first of all, if anything is moving in a circle, it has an inward acceleration. Just like if you're speeding up, you have a acceleration forward and you feel it on your back. If you're in a car, let's say, you feel the seat pushing back on you. If you're hitting the brakes in the car, you feel like you're getting thrown forward. That's a backward acceleration. Well, if you turn the steering wheel, you feel a throw to the side. So that's an acceleration. So whether your speed is changing or the direction of your speed is changing, you're going to get an acceleration. Acceleration is a change in velocity over time. If either the direction or the speed changes, you are accelerating, and you'll feel it in the car. Okay. Now, most of you probably remember the magnitude of the inward radial acceleration. We're going to call that a sub r. Okay, and that's just equal to v squared over r. Okay, and I'm going to put the magnitude sign there. That's how big it is. The direction is always inward in the circle. So one thing you're going to always do is when you have a problem, you're going to look and see, oh, at this moment in the problem, where the object's at this spot, which way is inward? And that's the direction this acceleration will point. Okay. You also might have done something like this last year. Net force in the radial direction equals m times ar, and ar is v squared over r. Okay. So this actually makes some problems in Newton's second law easier. Net force equals ma. Well, now you have an equation for that a. You can actually calculate it. Okay. Whereas in previous chapter, sometimes you couldn't do that. Okay. Now, in addition to this, there can also be a tangential acceleration. You probably did not do that last year. Tangential acceleration means, hey, is the car speeding up or slowing down as it's turning? So you could be going in a circle and speeding up, in which case you're going to have both the radial acceleration and the tangential acceleration. So there'll be a few problems here where I'll have that for you. Now, if we were in class right now, basically I would tell you that's it. That's the entire chapter 6 in the book. It's just, that's it. You probably want to see a few examples, I imagine, but honestly, this is the only addition to Newton's second law that you need to solve all the problems in this chapter. This is it. The equations are really simple, okay? So I'll start with an example, okay? So let's say that your little brother or sister is swinging on a swing, okay? So here's the chains. Here's the actual swing, and we're going to model your brother or sister as a dot or a circle there. And I'm going to give you a bunch of data. So let's say right now the swing is some angle to the vertical, theta. The radius of the swing is r, and they're moving toward the bottom at some velocity v. And I'm going to give you numbers for all that stuff. So let's say the mass of your little brother or sister is 40 kilograms. Okay, so that's about 88 pounds. The angle they're making with the vertical at this moment is 30 degrees. The radius of the chain is 2 meters. And the velocity at the moment pictured is 5 meters per second. Okay. What we're going to determine in this example is we're going to determine the radial acceleration at this minute, the tangential acceleration at this minute, because as you can probably tell, as they're on their way down, they're speeding up. Okay. And then what's the tension in the rope, or the total tension in the two chains combined. And then one more thing, the rate at which they're speeding up. Okay, so if the book were to ask you, at what rate are they speeding up? Okay, how would you answer that? All right, so let's start with how do you solve all these problems, okay? Well, AR we can calculate right now. AR is simply V squared over R, okay? And that is 5 squared over 2, which is 25 over 2, which is 12.5 meters per second, which is a little more than gravity. Okay, gravity is 9.8, so we're about 27% more than gravity here. Now, that's the easy one, so we check that off our list. Now, the rest of them, we're going to need to draw FBDs to do this. And again, I will draw the two FBDs. First, I'll draw like what are the actual forces acting on the rider. So this would be the College Board FBD. So first of all, you're on Earth, so there's going to be a force of gravity, which is mg, right? And then the only other thing touching the rider is, or the swing in the rider, are the ropes, which kind of pull that way. That's their force of tension, okay? Now, just like the last unit, what we're going to always do is we're going to break our forces down into components that are parallel to the motion and perpendicular to the motion. So I'll kind of draw some dashed lines for that, okay, on here. So here is parallel to the motion at that moment, and here is perpendicular to the motion at that moment, okay? Lucky for us, tension is already perpendicular to the motion, so we don't got to do anything with that. So I'll kind of redraw this here. So here's your force of tension, which is at a 30-degree angle to the vertical. Force of gravity, we got to split that up, right? So here you're going to have mg, and I hope you'll agree this is also 30 degrees there. So this is mg cosine 30, and then this component here is mg sine of 30, okay? So that's your FBD broken up, and again, every problem we're going to do, and that's one thing you're going to figure out your problems is, hey, which way is parallel to the motion and which way is perpendicular to it, okay? Now, we're going to go ahead and do the tangential acceleration next, okay? So the only force that's tangential to the motion is mg sine 30. So if I do net force in the tangent or parallel direction equals ma in the parallel direction, okay, the only force there is mg sine theta, and that's equal to ma tangential, okay, and I'll write a tangential. The m's drop out, which is kind of nice, and you have your answer. A tangential is g sine theta, and if you plug in 9.8 sine of 30, you're going to get 4.9 meters per second per second. So that's the rate at which the kid is speeding up as she speeds up on her way down. Okay, so that part's easy. Now, by the way, we've also answered the last question. The rate at which she is speeding up, it's the same thing. That is what tangential acceleration is. It's the rate at which you're speeding up or slowing down. So that's what you have. Okay. Now, as far as the tension goes, okay, the first thing I'll say is before I solve the rest of this problem with you here, there is a tendency and a misconception to say, oh, the tension is going to equal mg cosine theta, and that's it, I'm done. All right, no, the tension does not equal mg cosine theta. Here's why it does not. This person is accelerating inward. There is an acceleration inward toward the center of the circle, which is along the direction of the tension. Because there's an acceleration inward, there must be a net force inward. Well, if there's a net force inward, then Ft cannot be equal to mg cosine theta. Otherwise, the net force would be 0. Okay, so that's one thing. Secondly, hopefully you've ridden on a swing before, and you know that when you're swinging, you usually feel heavier than when you're still. If you're just sitting still in the swing, you feel your weight on the seat. You feel the normal force of the seat, really. If you're swinging, you feel heavier. That's the tension you're feeling. You're feeling that heaviness. That is this tension force getting bigger to keep you going in that circle. Okay, so they can't be equal. Okay, so what we're going to do is we're going to do net force in the perpendicular direction, which is radial, equals ma in the perpendicular direction. You always make inward positive. So toward the center of the circle is positive. So if I do that, I've got Ft minus mg cosine theta equals m, and the acceleration that's perpendicular is the radial acceleration. That's your perpendicular acceleration, which we have a number for. It's 12.5. Okay, so we got everything here. Ft minus m, which is 40, times g is 9.8, cosine of 30 equals m, which I know would be 40, okay, times ar, which is 12.5. Now I want to mention something here. At this point, you would just plug and chug, but I do want to go ahead and say something. This number here, that's the weight of the kid okay? And if you plug that in your calculator, you should get 392 newtons, okay? What you're going to notice is when we solve for Ft, it's going to be more than that, all right? So in your calculator, you would take 392 times cosine of 30, and you would get 339.5 equals, and 40 times 12.5 is 500, okay? And so your Ft, you add them up, and you get 839.5 newtons, okay? Which is a lot more than the kid's weight. It's more than double the kid's weight. So the kid would feel really heavy at this moment, okay? Now, so there's your first example. Now, one last thing I'll mention about the intro here. Remember, Newton's first law. If you really understand Newton's first law, that'll help you understand circular dynamics. In that Newton's first law says things want to go straight. So this girl in the swing, she wants to go straight. So going back to our picture here, she wants to go this way. The swing is making her accelerate that way, away from that straight line path. So there's this inward acceleration, that's your radial acceleration. If that wasn't there, if there wasn't a force to pull her into a circle, she would indeed go straight, okay? All right, so the next couple of videos, there'll be some more examples for you to look at, but they're all going to be the same. You're going to split your forces into parallel and perpendicular to the motion. You're going to look at the tangential acceleration. You're going to look at the radial acceleration, and then you're going to solve for whatever they're asking you to solve for. I hope that was helpful, and thanks a lot.